Hello everyone, and welcome to today's Chem lesson. Today we are going to begin a new unit, our Math of Chem unit, and we're going to start by diving in and looking at the concept of a mole. Now, when we talk about a mole in chemistry, we're not talking about the furry rodent that lives in the ground. We are talking about a word that means a number. This shouldn't be a new concept for everyone, because you go to the store to buy a dozen eggs. Right? We have in our vocabulary already a large amount of words that mean numbers. If I say, I have a dozen eggs, you know that I mean that I have 12 eggs. If I say that I have a pair of cats, you know that I have 2 cats. If I say that I have a trio of puppies, you know that I have 3 puppies. Right? We know already a bunch of words that mean numbers. You've likely never heard a mole before, because it's a number that is very specific to science and chemistry specifically. A mole means 6.02 times 10 to the 23rd. It is an absolutely ginormous number. But it can be used in exactly the same situations as a dozen or a pair or a trio. Right? I have a mole of eggs. I have a mole of cats. I have a mole of pennies. It's just a word that means a number. Now, Mr. M, what's special about this number? I hear you ask. And this number is special because it's actually going to help us convert from AMU to grams. Alright, so let's break it down piece by piece and see why that's important. On the periodic table, if we look at any box, we see a number of pieces of information. We're going to focus today in on this piece of information here. This number is the atomic mass. And when we look at the atomic mass, we know that that means the average of every isotope, right? The weighted average of all the naturally occurring isotopes make the atomic mass. And that's what one atom, on average, weighs. One atom of oxygen weighs 15.999 AMU, right, which is atomic mass units. Now, talking about something at the scale of one atom is absolutely teeny, teeny, tiny, right? We can't pick up a single atom and combine it together with something else to make a compound. Right? We don't have tools that can see that small consistently enough for us to actually do anything important with them. Right? But what we do know is converting. Right? We can say 1 mole of oxygen atoms, right, an insanely large amount of something insanely small makes a regular thing. Right? If we take the smallest number and the largest number and, use them in relation, they're going to kind of cancel each other out and meet in the middle. And that's where we're going to end up. We're going to end up with 15.999 grams, which is a pen. Right? That's something that you can see and manipulate. that is an amount of a substance that's easy to work with as human beings. So the mole is a super important number. This number, 6.02 times 10 to the 23rd, is the number of atoms that is needed to take the mass from AMU, right, from teeny, tiny number, to make it the mass in grams, a regular number that we can work with, a regular weight and a regular mass that we can work with. And it's worked out in such a way that the number doesn't actually change. 1 atom of oxygen weighs 15.999 AMU, but 1 mole of oxygen atoms weighs 15.999 grams. Right? This numerical value stays the same. We're changing the unit when we talk about a mole of something, which means that this number is both the atomic mass and something called the gram formula mass. It's what 1 mole of that substance weighs. And this becomes insanely useful as we talk about doing chemistry in the real world. If we're going into a lab and we're trying to make something, we can't use AMU as our units because we can't get that small. We can't work on something at that scale. And so we need something that functions at a bigger scale for us to actually be able to talk about it. So we need this idea of the mole so that we can actually do chemistry. Let's look at some ways that this can be tricky. When we talk about a compound or a molecule, and we want to know what 1 mole of that substance weighs, we need to do some light math. All right, if it's just an atom, we can pull the number right off the periodic table. 1 mole of oxygen weighs 15.999 grams, which we're going to round up to 16. And we're going to start rounding to the nearest whole number. But here, H2, now if I want to know what a mole of H2 weighs, I can't just use I can't just use 1 atom of H. I have to use 2 atoms of H. So here it would be hydrogen plus another hydrogen. And when I check the periodic table, right, let's do that together. When I check the periodic table, hydrogen has a mass of 1. All right, 1.00794. We're going to round it to 1. And so when we come back here, we're going to have 1 gram and another gram for a total of 2 grams. When we have a compound with multiple different elements, we're going to have to reference both atoms. Right here we have H2O, which we know is H plus O. So we have 1 plus 1 plus 16. So if I want to know what a mole of water weighs, it would be 18 grams. And we can do that for every compound. Where it gets tricky is in something like this down here in calcium nitrate. In something like calcium nitrate, we have the parentheses here. And those parentheses are telling us that we actually have 2 copies of the nitrate. So we have calcium plus NO3 plus another NO3. we would need to take this apart further if we want to fully count it out, right? It's not just calcium and 2 nitrates, it's calcium, 2 nitrogens, and 6 oxygens. Pulling the whole thing apart to make sure that we have all the right pieces. So really there's 2 steps to this process. There's 2 steps to figuring out what 1 mole of something weighs. The first step is counting up the atoms. And the second step is using the periodic table to find the mass. So slowly, let's do an example. Right, we're going to start by taking it apart and counting how many of each type of atom is in the substance. Right, so the example up top here is the one that we were just looking at. Calcium nitrate has 1 mole of calcium atoms, 2 moles of nitrogen atoms, and 6 moles of oxygen atoms. I'd like for you to take a crack at these 4 down here. How many moles of each type of atom are in these substances? I'm going to leave about 40 seconds on the clock. When we take apart these 4 substances, we should end up with counts that look like this. For manganese sulfide, we have 2 moles of manganese atoms and 7 moles of sulfur atoms. Carbon tetrachloride has 1 mole of carbon atoms and 4 moles of chlorine atoms. Aluminum sulfate is the trickiest of the bunch here because of the parentheses. We have 2 moles of aluminum, 3 moles of sulfur, and 12 moles of oxygen, because the 3 is going to apply to everything inside the parentheses, right? We have 3 copies of SO4, meaning SO4 plus another SO4 plus another SO4 for 3 S's and 12 O's. And then lastly, carbon dioxide, 1 mole of carbon, 2 moles of oxygen. So that's always going to be the first thing that you do when you want to find out how much a mole of something weighs, is check, well, how much of each thing do I have? Then we're going to start caring about what the numbers are, right? What those masses are. And so we're going to stick with our same example of calcium nitrate. And I'm going to start looking at what each thing weighs by taking numbers off the periodic table. All right, let's look at this one together as well, right? I've got calcium, nitrogen, and oxygen. So let's find those masses. Calcium is right here with a mass of 40.08. Rounding down to 40. Nitrogen, 14.0067, which we're going to keep at 14. And oxygen with its 15.999, which we're going to round up to 16. Right, so that's where our 40, 14, and 16 came from. We're accounting, right? We have 1 mole of calcium, so we have 40. 2 moles of nitrogen, so 2 copies of 14 grams, so 28 total. and then 6 oxygens for 6 times 16, 96 total. When we add up all 3 of those together, we're going to get our sum total of 164, telling me that 1 mole of calcium nitrate weighs 164 grams. Let's look at the 4 examples from before and see if we can do the same thing. Right, here are those same 4. Right, our manganese sulfide, carbon tetrachloride, aluminum sulfate, and carbon dioxide. Can you find the actual masses of these 4 things? What does 1 mole of each of these things weigh? I'm going to leave about a minute on the clock here. Alright. If we want to find out what 1 mole of each of these things weighs, we're going to reference the periodic table and sum up our values to get these numbers. Using what we did before, right? 2 moles of Mn, 7 moles of S. Finding out what each of those things weighs and applying the correct numbers to get a total of 334. One thing I do want to reference and look at specifically is the CCl4 example. That's 1 mole of carbon and 4 moles of chlorine. And you may have done this example and come out with 152. And I want to tell you why 154 is written here. If we reference the table, we're going to get carbon with a mass of 12 and chlorine, right? Carbon with a mass of 12 and chlorine with 35.453. And chlorine is something that we actually cannot round to the nearest whole number. Chlorine is really the only one that we are going to round to the 0.5. So chlorine doesn't round down to 35, it rounds to 35.5. And that's where your missing 2 comes in, right? If you had 152, you rounded to 35, but the 0.5 times 4, the extra 2, is going to bring us to 154. There's no great reason why chlorine rounds to 35.5 and is the only one that does so. There are other elements that are closer, but that's just the way it is. We can use the idea of gram formula mass, the idea of what 1 mole of the substance weighs, to then solve other problems, right? This is going to be something that we get to use moving forward. Let's look at an example of that. Right? If I have just a mass of CO2, right? If I say that there's 86 grams of carbon dioxide and I want to know how many moles there are, I have a conversion. I know, right, because I just did it, that 1 mole of CO2 is equal to 44 grams. And just like when we talked about dimensional analysis, I now have a conversion factor. Specifically for CO2, I can plug things in to figure out if I have 86 grams, how many moles is that? Before we do any math, we can use a little bit of common sense and say, well, if 1 mole is 44, 2 moles would be 88. We have 86. So I'm thinking a little bit less than 2 moles should be the number I come up with. We can plug in values. Using our dimensional analysis, something that will cancel out grams but keep moles. And end up with a number that's 1.955, which is exactly what we expected. A little bit less than 2 moles. There's no wrong way to go about your math as long as you get the answer, right? You don't have to use dimensional analysis. You'll never have to use dimensional analysis. If you want to set up a proportion instead, 86 over x equals 44 over 1, and solve a proportion, that's also fine. You'll still get the same answer. Right, but we can convert back and forth between moles and grams because you always know what 1 mole is equal to. As we move through the unit, we're going to be coming and using these numbers, this idea of a mole, over and over and over again. Right? It is the foundation for all math in chemistry. And so as we explore more mathematical chemical options, we will be seeing the use of a mole and gram formula mass throughout. But for now, I'm going to ask for everyone to transition over to our Google Meets for questions, comments, concerns, and attendance. And I'll see you there.